All right, today we're going to be talking about the second fundamental theorem of calculus. So yesterday we did the first fundamental theorem of calculus, and today we'll do the second one, and there are only two. So this will be the end of the fundamental theorems of calculus. All right, I'm just gonna write a problem on the board, and then we'll talk about how to solve the problem, and hopefully it should be like semi-intuitive, but here's the big idea. The main thing that I want you to pay attention to today is to actually look for patterns, okay? If you look for patterns, you can make these problems a lot easier on yourself than if you just kind of try to work them all the way out every time. There is a super easy shortcut to being able to work these problems, and it's one that hopefully you'll just be able to pick up on without too much trouble. Okay, so let's start with something that looks like this. And when you see that right there, like that looks like a bunch of gibberish, okay? Like it has no meaning whatsoever. But it's actually a really simple problem, and hopefully you'll see what ends up happening. And just to kind of get you to be able to work these, all I'm going to do is I'm just going to work several examples, okay? And as we work examples, you're just looking for a pattern the whole time. So I'm just going to work example after example after example, and then you look for patterns, look for patterns, look for patterns, and then once you get the patterns, we'll just start using the patterns, and we'll make this a very simple process, okay? Then we can talk about a little bit of notation, a different way to do it, and go from there, okay? But here we go. This right here, what does this first symbol right here mean? What is that telling us to do? Take the derivative. That's exactly right. So take the derivative of what? Well, then we have this thing right here, which is a what? An integral. Now, involved in an integral is a what? What's one of the main steps in finding an integral? An antiderivative. So this problem has us both taking a derivative and an antiderivative, which means we should basically get back where we started, right? Because, I mean, if you take a derivative of a function and then you take the antiderivative, you get back to where you started. If you take the antiderivative and then the derivative, you get back to where you started. So here's the thing that I want you to notice right now, okay? This is our function, and our notation is important here. Notice that we have a u, so we're going to take the, now, think of this as order of operations with calculus, okay? So this is our function, and the u is what we're going to take the antiderivative of, stuff with respect to u. That's why we have our du back there. But in calculus order of operations, what you always want to do is the thing nearest to the function, okay? So right now, this is actually, if you want to consider that inside of parentheses, because the integral is right next to the function, the first thing that we want to do is take the integral. Okay, so we're going to take this integral, and then after we've taken the integral, then we will take the derivative. But I'm going to try to carry my notation out the whole time here, just so you can see what's going on. So we're going to take the derivative of, okay, so that just stayed the same. And now let's actually do some work on the inside of this parentheses. What is the antiderivative of 2u? Okay, so now we have u squared evaluated from 0 to x. Okay, is everybody okay with me changing the antiderivative in that way? Okay, so u squared evaluated from 0 to x. And now I actually want to take care of the evaluation. So this is the change with respect to x of, and now I'm just going to plug in. So this is x squared minus, and when I plug in the 0, I get 0 squared. So I'm taking the derivative of x squared minus 0 squared, which is really just the derivative of what? And we get, yeah, 2x. The derivative of x squared is 2x. What was our function to start with here? 2u. And then we took an antiderivative and then a derivative, right? And guess what we have? The exact same function. The only thing that's changed is what? The variable. That's exactly right. The variable changed from a u to an x. Okay, that's all that's basically happened when we took that antiderivative and then a derivative back to back. Okay, so let's say I have something like this then. going to use a different, here, 5. Okay, so I want to take the derivative with respect to x of the integral from 5 to x of sine of u du. Okay, so this is the derivative with respect to x of, and now what's the antiderivative of sine? Negative cosine of u, and we're evaluating from 5 to x. Okay, so evaluating from 5 to x. Okay, so let's go ahead and actually plug in to be able to evaluate this. And so we're going to be taking the derivative with respect to x, and now we have negative cosine of x minus negative cosine of 5. Okay, so this is the derivative with respect to x of negative cosine x plus cosine of 5. Now, what is the derivative of negative cosine? Sine x. What is the derivative of cosine of 5? 0. Why is it 0? There's no variable anywhere. This is a constant. You can put cosine of 5 into your calculator if you want to, and you can change it into some decimal number, right? Just because it says cosine does not mean that we're dealing with a variable there. So that's just a constant. So when we take the derivative, it goes away. So we're left with sine of x. Okay, so sine of u was our original function. We took an antiderivative within that integral. Then we turned right back around and took the derivative, and we ended up with sine of x. All that happened was the variable changed, right? Okay, so Samir. Okay, so do we just stick with the original function every time and put the upper bound in for the variable? Okay, well, there are a few things that you're picking up on there, and that is part of the pattern. Okay, that the x value for the bound just gets put in. But the thing that I want to note here, what is the similarity between the lower bound in this problem and the lower bound in this problem? Yeah, they're both constants. So no matter what, whenever we take an antiderivative and then we plug in a constant, right? We take an antiderivative and we plug in a constant. When we turn back around and take the derivative, what's going to happen to that constant? It's going to go to 0, right? So whenever we go to take a derivative, you can see in this one right here, we plugged in, this is where we plugged in the 5, right? What happened to this thing when we took the derivative? It went away. Come back to this one right here, okay? This is where we plugged in the 0. Well, it actually went away before we could even take a derivative, but if we waited to take a derivative, it would have gone to 0. So whenever we plug in a constant, because we're about to take the derivative, and we have a constant plugged in, well, then when we go to take a derivative of it, it's just automatically going to go to 0. So these things down here, these constants, end up not even mattering. And so that's why Samir is saying, hey, the upper bounds, we just traded those out. I put that x in for a u, and in this one I put that x in for a u, and that is in general what's going to happen, but we have to be careful about it. The reason these went in was because they were an x value, okay? Not because they're the upper bound, it's because they're a variable. And the reason these went away is not because it's a lower bound, it's because it was a constant. And what happens when you take the derivative of a constant? 0, it disappears, okay? Jacob. Okay, that is a fantastic question. What if we had x to 5? Anybody want to make up a function? 3u squared du. Okay, great. So that's the function we'll use. 3u squared will be our function. Okay, so take the derivative with respect to x of, And then what's the antiderivative of 3u squared? U cubed. That is exactly right. And we're evaluating from x to 5. So now what do I plug in first whenever I go to evaluate? The 5. So this is 5 cubed minus x cubed. So now if we take the derivative of 5 cubed, what do we get? 0. And negative x cubed becomes what? Negative 3x squared. Okay, well then that's a little different from this original function we had. The original function had 3u squared, and this one right here has negative 3x squared. Okay, so the variables changed, but the function turned from positive to negative. Why did it do that? Because the x was where? It was the lower bound this time, right? So the 5 disappeared just like we expected whenever we plugged it in because it was a constant, so it disappeared. But then, whenever we plugged in the x, it was on the lower bound, and what do you always do with the lower bound? Yeah, look at what you always do with an antiderivative when you evaluate that lower bound. You subtract the lower bound. So it comes as no surprise that this thing right here just turned negative because now we were subtracting that lower bound, right? Does that make sense? Okay, so let me give you something that looks like this. Let's just try a few of these simple ones and see if you can tell me exactly what they're going to be. Uh-huh. 7u minus 5. This is the function. Okay, let's skip all the work and just use a pattern. What's this going to be? It's exactly right. I'm going to say always. We're looking for patterns, right? There's more to the patterns than just plug in an x, right? Right, but there's more to the pattern than that, okay? So in this one, that worked, okay? But we want to observe a little bit more so we can learn more about what's actually happening in these patterns, okay? Very good. Let me throw another one up here real quick. Say that again, Abigail. Yeah, E's still a constant. So is this thing going to matter down here? No. Okay, so. Done. Easy enough? For now. Right, for now. Okay. Done. But this one just turned negative. Why? X was on the lower bound. Okay? Easy enough? Okay. I think we got established a pretty good pattern with those. Okay, so let me... Yeah, so now let's make it a little more difficult. Can what? No. All right. So this right here, we're going to take the derivative of And now so we got to take this integral first though, right? So the derivative of the integral. We're actually going to work this one all the way out. We're not going to use a pattern on this one yet. We need to work this one out because we haven't seen anything like x squared. Okay, we've only seen x's. So x squared may behave differently, so we should see what happens here. Yeah, the antiderivative is cosine of u. And we're evaluating from 5 to x squared. So does this come as any shock to anybody that we're about to take x squared and plug it in where u was? Right? No, that shouldn't come as a shock, okay? So we are about to do just that. We're going to take x squared and plug it in where u was. So just like you would normally expect, that thing gets substituted in for u, okay? But we're taking the derivative of that, minus, since we're minus our lower bound, so minus the cosine of 5, okay? So that's what we've got. And whenever we go to take the derivative of this, okay, when we go to take the derivative of this, then what is the derivative of cosine of x squared? Negative sine of x squared times 2x, because we have to use what? The chain rule. And then what happens to cosine of 5? Yeah, it disappears. Okay, so this is what we end up with. Now, the negative sign of x squared is totally expected. Okay? The negative sign of x squared is completely expected because we had negative sign of u. So the x squared just went in for the u like we expected. But where in the world, where did this 2x come from? Yeah, it came from the derivative. Because 2x, okay, because x squared is what's inside of the sign, whenever we go to take the derivative, we're going to have to use what? The chain rule. That's exactly right. Because the x squared is on the inside, we're going to have to use the chain rule. And now when we use the chain rule, we get this 2x on the outside because it is the derivative of what? X squared. Okay? So what actually happened is we plugged the x squared in, and then we had to do what? Multiply by the derivative of the x squared, which is 2x, because of the chain rule once it got plugged in there. Okay? Did we do that in these problems? Where did these go? Of course we did it in those other problems. The only difference is that the derivative of what we plugged in those cases, since it was just an x, the derivative was what every time? 1, so it didn't change anything. But now the derivative of what we plugged in, when we get to this one right here, is 2x, and so it actually changes something. From 5 to x squared of u to the third du. Let's find out. Okay, so the change with respect to x of, and then what's this antiderivative going to be? U to the fourth, evaluated from 5 to x squared. So this is the derivative of 1/4 x squared to the fourth minus 1/4 times 5 to the fourth. Okay, I'm going to leave this. Okay, this is going to look really ugly, but I'm going to leave it like this, and I'm not going to simplify this front piece right here, just so it'll keep it in a form that'll be easier for us to kind of diagnose what happened, okay? So I'm actually just going to use a chain rule with this. Okay, so what's on the outside of this function right here? The 4. So I'd multiply by the 4, and I would get what? This would turn into a 1 because the 4 times the 1/4. So I leave the inside alone and then subtract 1 from the power, and it gives me what? 3. So I did the 4, and now I should take the derivative of what? The inside, which would be 2x. And then what's the derivative of this stuff back here? 0. It's a constant. So that derivative is 0. So this is what we ended up with. Okay? So let's take this. I'm going to take it up top. Top's not that far, huh? Okay. So, and compare it to what we have right here. Well, it looks like we took the x squared and did what with it? Plugged it in for u. There's x squared to the third. It was u to the third, and now it's x squared to the third. But now there's what out here? 2x. Again, where did the 2x come from? It came from the chain rule, because when we plug that x squared in there, when we go to take the derivative, the chain rule is going to require us to multiply by the inside, the derivative of the inside. And does everybody see that what we're doing, that x squared that we're plugging in every time becomes the inside of the function? And when you take a derivative, the chain rule says it's a normal derivative, and then you take the derivative of the inside. Well, since this x squared is what we keep putting on the inside, it comes as no surprise that its derivative always ends up being multiplied, because by the chain rule, you multiply by the derivative of the inside. And so that's why that 2x keeps popping up right there. And so this is exactly what we would expect, right? This stuff, x squared to the third times 2x. And now if we really wanted to clean this up, what is x squared to the third power? This is x to the sixth times 2x, which is 2x to the 7th, okay? But if I went ahead and wrote it as 2x to the 7th, you would have looked at me like I was crazy and be like, how does that have anything to do with what we have there, right? So that's what we've got. Okay, so we plugged it in and multiplied by its derivative, dx, and I'm going to use from -2 to 2x. Sure. What's up? Okay. And let me create this function. I don't know, I'll use a trig function. We'll just use cosine of u. Okay, so the derivative of, and then if we take this antiderivative, what's the antiderivative of cosine? So sine u evaluated from -2 to 2x. Sine 2x minus sine -2. What is the derivative of sine of 2x? 2 cosine of 2x. And then the derivative of sine -2? 0, right? Piece of cake. Now, plugging the 2x in for u, we completely expected, because if you go back and look at the top, the 2x just went right in for the u, okay? But where did the 2 come from? It's the derivative of the 2x. Okay, so do we think we can maybe establish a pattern now? Okay, what are we doing every time? And what do you do with the derivative? You just get it? You multiply by it, right? So we plug in, and then we multiply by the derivative of what we plugged in. Okay, so let me give you one that looks like this. And we'll try to do this one with a pattern. All right, check out this lower bound. What is it? More importantly, a constant. So what's going to happen to it? It's going to go away, right? But this sine x, what should we do with it? Plug it in. So this will be sine squared x, right? So u squared, but u is sine now. We plug sine in for u, so it's sine squared. But then what do we need to do? And what's the derivative of sine x? Cosine. What should we do with the derivative of this thing that we plugged in? Which would give us cosine x. Okay? Plus. Everybody okay with that? No minds blown so far? Use the pattern. We'll use a pattern. What do you notice about this 100? Constant. So it's not going to matter, right? Because we're going to be taking a derivative, and so constants will all disappear when we take the derivative. This thing is on the what? Bottom. What do you always do with the lower bound in an integral? You subtract. Well, then we're going to have to subtract whatever's happening with this 3x squared because it's from a lower bound. We take that 3x squared and do what with it? So this is the natural log of 3x squared. But then, according to the chain rule, when we go to take that derivative, we're going to have to do what? Multiply by the derivative of the inside, and we know that the 3x squared is going to be the inside because that's what we're putting in there, right? So what's the derivative of the inside going to be? 6x. Yeah. Right. If it's a derivative of an antiderivative, okay? If it's just an antiderivative, then yeah, you got to take it. But if it's a derivative of an antiderivative, then this is what's about to happen. Now, that's the whole idea behind the second fundamental theorem of calculus. If you take a derivative and then you take an antiderivative, where you get? Back to where you started. That's exactly right. And in this case, antiderivative and then a derivative. You're just back to where you started, okay? So that's the thing that they're trying to reinforce. The only nuance is the way that the chain rule would affect that problem whenever you're going through it. Okay. I mean, you could, if you were given something like this. Sure, write this one down. It'll be easy. Same rule, right? We take this and do what with it? Oh no, I cleared my ink. There we go. Okay, we take this and do what with it? Plug it in. So sine of x over x plus 1. That is correct. We need to find the derivative of x plus 1. And so we would get low d high minus high d low all over low squared. Okay, so this is sine of x over x plus 1. And then if we distribute this 1, we get x plus 1 minus x over x plus 1 squared. These two x's cancel one another out. So it's sine of x over x plus 1 times 1 over x plus 1 squared. Okay, but it's not going to be a quotient rule in the sense of like these two things are being divided. It's the chain rule because that thing that you plug in keeps going where? To the inside of a function. You plug it into the function, right? You plug it in, and whenever something's inside of something else, that's when you have to use the chain rule. okay? It's not like this thing is going to be divided by. Well, then we would want to be using the quotient rule with it. But that's not the case. It always goes inside of the function, so it's consistently the chain rule, okay? So we're always multiplying by the derivative of the inside. Okay, so let me give you something that you haven't seen before. dx. Now we have variables in both spots, right? So we don't have any constants to be able to get rid of. So what do you think we do? Just do the same thing, except we're going to have an upper bound and a lower bound in this case. Okay? So for the upper bound, what would I get? I take the 3x squared and do what with it? Plug it in. So this is cosine of 3x squared. But then according to the chain rule, I have to take the derivative of what's on the inside. And what went on the inside right here? The 3x squared went on the inside. And what is that? Yeah, the derivative of that is 6x. So this is 6x cosine of 3x squared. And then minus, that's exactly right, cosine of x. And it, we could do the same thing with the chain rule, but the derivative of that x on bottom is just what? 1. So if we multiplied by that 1, doesn't change anything at all, right? Identity property of multiplication. So that's it. This is about as complicated as it could get, okay? We'll do one more. I'll try to make this one really complicated so that I know if we get it, then we're good. Five x squared plus x, yeah, is the upper bound. 5x squared plus x. Okay, but we know the pattern, right? So all I got to do is just stick to the pattern. Okay, so somebody tell me what you think you would get for this. Five x. Yeah, that's all x's, nothing but x's. Yeah, that's 5x squared plus x up top. And my calibration's off, so it's not going to let me do it. So here. Yeah, go ahead. All right, so cosecant. All right, so you're saying 10x plus 1. So there's your derivative of this thing. Okay, times cosecant squared of
5x squared plus x plus 3 minus.
Yeah, and then minus
Cosecant squared of 2 sin x plus 3.
times cosine x. Because we have to do the derivative of this thing down here as well, right? So this is what we have. This is 10x plus 1 cosecant squared of, and I'm going to distribute that 2 now, 10x squared plus 2x plus 3 minus, and I'm just going to throw that cosine to the front, cosine x times cosecant squared of 2 sine x plus 3. Okay, so is everybody okay with how I got this? Okay, this right here is the derivative of the upper bound. That's how we got the 10x plus 1. Then we take, cosecant squared. With this upper bound just goes in for u. So this next piece right here, okay, is just the same function, cosecant squared of 2, and then we have 5x squared plus x plugged in for u. So we just plug that in for u. And then the plus 3 is like there just like it was in the function. Plus 3 in the function, plus 3 down here. Minus, because now we're dealing with a lower bound, and all we did was take sine x and plug it into this function. So it's cosecant squared of 2u, and so we have 2 sine of x instead of 2u now. And then the plus 3 is there just like it was before. But then because we plugged in, the pattern we've talked about is you need to multiply by the derivative of what got plugged in, and that what got plugged in was sine, and so its derivative is cosine. Okay? And from there, I just cleaned things up. I just brought that 10x plus 1 down. This 2 was distributed on the inside here, so this is cosecant squared of 10x squared plus 2x plus the 3 is still just hanging out, right? Minus, and all I did was move this cosine to the front, so cosine of x, cosecant of 2 sine of x plus 3. That's it. Okay? All right. So now we'll practice some problems just to do some exercises in class, and then I'll give you guys your homework.